Hi, everyone. So, in terms of a large part of the difficulty in OChem is also just like, aside from mechanisms and synthesis, a large part of it is just being able to organize and really get to know all of the reactions that you have at your disposal in order for this exam. So for this video, we'll be trying to organize all of the reactions we know and looking at the products and just taking a general broad view of the different reactions we've learned. And so this isn't a replacement for your own studying, but I did want to just kind of organize reactions based on essentially you start from an ether, for example, and what are the reactions you can do starting from an ether. Okay, and so just as a reminder, if you haven't already, please sign in for this review session. The link to sign in should be on the first video in Michaela's section. Okay, anyways, let us start. So the first category I wanted to go over is ethers. And so the first reaction that ethers can undergo is autooxidation. So when you undergo autooxidation, right, this is due to oxygen in the atmosphere. And this can go through, or this can be done on any type of ether. And so in terms of what you get, this would be the major product where you get, remember, this is a radical mechanism. I highly recommend that you review that. And then we get this, essentially a dimer, as our second product, which is the minor product. Okay. And so the next reaction is nucleophilic additions to epoxides. And so under basic conditions, right, this is basic because of the NH2. Under basic conditions, we'll add our nucleophile to the least hindered side. Okay. Okay. And in contrast, under acidic conditions, is acidic because of HBr or H2SO4 or something like, or an alcohol, for example, then we would add our nucleophile to the more hindered side. All right. And then the next reaction we can do with ethers would be Grignard addition. Okay. And so with Grignard addition, essentially, we are adding our carbon nucleophile to the least hindered side. Okay. Because remember that Grignards are basic, right? And so as a result, we will do basic conditions for this attack to an epoxide. And in this case, it will be the least hindered side. All right. Moving on to alkenes. Okay. So the first reaction we know of for alkenes would be oxymercuration and demercuration. This is essentially all just to create an alcohol on the more sterically hindered side. For ozonolysis, right, we remember that this is essentially just the cut in half method, but there are two different types of ozonolysis we've learned. There is the reductive ozonolysis, which involves a dimethyl sulfide, and what we get is essentially aldehydes and ketones. But in this case, the product we get are specifically just aldehydes. Okay. We can also do an oxidative workup, which involves H2O2. And in this case, instead of having H's on our aldehydes, we instead get alcohols. And as a result, we make carboxylic acids. All right. Next up, we have Mcpba epoxidation, okay? And this, as the name suggests, we just create an epoxide from our alkene, okay? afterwards, we have halohydrant epoxidation. So this is just a different way. It's a two-step way to make an epoxide. So we start off with NXS. This could be NBS, NCS, or NIS. And essentially, X is just a halogen. Okay. And so by doing that, we get a vicinal halohydrin. Okay, so the halide will be on one side, and we get OH on another side of the alkene from H2O. Okay, and this is our vicinal halohydrin. Okay, and then upon treating this with a base, we'll deprotonate this alcohol, and from there, we get our epoxide. Okay. All right, and so that should be all the reactions we know of for alkenes. Let's move on to alcohols. So the first reaction would be acid catalyzed ether synthesis. And just a reminder that this only works for primary alcohols. And so in this reaction, we're essentially just dimerizing our primary alcohol. So this is the first, so this is our alcohol. And then we can just erase and then put another carbon backbone onto it. Okay, and remember, this only works for primary alcohols, and we get H2O as a byproduct. Okay. Now, for chlorination and bromination using a strong acid, okay, we can do this on secondary, tertiary benzylic and allylic alcohols. And so, as the name suggests, we just replace our, in this case, benzylic alcohol with a benzylic halide, in this case, chlorine, because HCl. Now, we can also do bromination on primary alcohols, but not chlorination, because remember, HCl isn't a good enough, or chlorine isn't a good enough nucleophile to go through this reaction. And so therefore, with primary alcohols, you can only brominate with a strong acid, right? And so another way we can brominate an alcohol, specifically for primary and secondary, we can use PBr3. And so in this case, we replace our alcohol with bromine, okay, and we maintain the stereochemistry. Okay, and then for chlorination with SOCl2, there is two versions of this. There's the no inversion, or there is the inversion, okay? And so with just SOCl2, we will maintain our stereochem. So in this case, we go from a dashed OH to a dashed chlorine, whereas with inversion, that's when you have pyridine, which is this molecule right here, we observe an inversion in stereochem. So in this case, we go from dashed OH to wedged OH. Right. So the next reaction we know of is tosylation, mesylation, and triflation. So respectively, that's TSL, MSCl, and TFCl. Right? And so what we get is essentially we maintain our stereochem and we attach. So first we have the alcohol. So the O stays, it's just the H that's replaced. And we put TS for the tosylate. We put OMS for our mesylate. And we put OTF for our triflate. Okay, and remember that stereochem is maintained. Okay. Now we have silyl ether protecting groups. And so essentially we take this protecting group right here, the silicon chloride, essentially. And so we're going to attack the least substituted because of steric hindrance, okay? And so we just essentially replace the chloride on that silicon molecule with the oxygen, okay? And so we go from here, and then the O, and we get this molecule right here, okay? to replace the chlorine with an oxygen. And then you can do the reverse reaction, because remember this is a protecting group, and then you just use Bu4NF and you get your original alcohol. Next, we have alcohol oxidations, okay? And so with alcohol oxidations, we are essentially going from alcohol to a carbonyl. So with primary alcohols, we get aldehydes. For PCC and PDC and Swern. But the main difference is that under Jones oxidation, we get an alcohol, or a carboxylic acid. Okay. And then just as a reminder, these are all primary alcohols. However, for a secondary alcohol, right, we will observe go from a secondary alcohol to a ketone with Swern, PCC, PDC, and Jones oxidation. Okay. All right, let's move on to alkyl halides. With alkyl halides, the first reaction we know of is Williamson ether synthesis. So in Williamson ether synthesis, right, we are essentially replacing that bromine right there, okay, and we are going to replace it with our oxygen, our charged oxygen species, okay? And so in this case, we get the oxygen tert-butyl onto our alkyl halide, and as a result, we form an asymmetrical ether. Okay. Next reaction would be crown ether fluorination. So remember that fluorine is a terrible nucleophile, but with the assistance of a crown ether, in this case 18C6, we can have fluorine act as a nucleophile, and we have a basic SN2 reaction where the bromine is attacked by fluorine, and we get a fluorinated product. Okay. For our next reaction, we have preparation of organometallics. So we start off with a primary, secondary, tertiary, or aryl alkyl halide. And so upon treating it with 2 lithiums under a cold environment, we're going to get our organolithium. Okay. We can do something similar for Grignard. So we just use this on primary, secondary, tertiary, aryl or vinyl alkyl halides. And then from there, we create our Grignard. So we attach a magnesium, and the bromine from that alkyl halide will stay. Okay, let's do the next reaction. Okay, so with a Lilyc halogenation, we would use, again, NBS, NCS, or NIS. Those, please review what those structures look like from your notes, okay? But essentially what we're doing is we're going to take that allylic position, which is right here, and we're going to add our halide, okay? And this undergoes a radical mechanism. The next alkyl halide reaction would be the Wittig reaction. This is on primary and secondary alkyl halides. And so the first step from the alkyl halide is to create our phosphorus ylide, okay? And so with that, we're going to use PPH3, and in the second step, use a butoxide. And so from here, we're essentially going to replace that bromine with PPH3, and then this potassium butoxide is going to deprotonate the carbon next to that phosphorus and create a negative charge, right? And since phosphorus has 4 bonds to it, it'll be a positive charge, okay? Remember to review this from your notes. And so upon giving our phosphorus ylide a aldehyde, right, or a ketone, if you'd like, then we create an alkene, okay? It will look like this. And so remember with Wittig, we get the cis alkene selectively. In order to, or as a contrast to that, we have the Horner-Wadsworth-Emons reaction, okay? This will give us the trans alkene version. And so the main difference is that we use a phosphate ester right here and NaH as the base. And so what that means is we're going to, instead of replacing it with the PPH3, we're going to replace the bromine with a phosphate ester as so. Okay. And in this case, the NaH is going to deprotonate that molecule right next to it, okay, right here, the hydrogen next to the phosphorus ester. And then so this will be our phosphorus species, which we will react with an aldehyde. And here we are going to get the trans product. Okay. Okay. And so that should be it for our allylic halides.